We looked at the change in reactions and we saw that you can have differences in energy between the reactants and the product, and we can define it as being exothermic or endothermic, and that there's an activation energy, an energy hump between the reactants and products. This activation energy is very important because that determines how fast the reaction will go. If you have a high activation energy, few molecules have enough energy to give up to get over the hump, and so you have a slow reaction. If you have a low activation energy, most of the molecules are going to have enough energy to change into, breaking bonds, that the reaction will go very fast. So the rate of reaction is determined by the activation energy, but it's also determined by the number of collisions and the temperature. Because if you change the temperature, you're changing the energy available to the molecules. And if you have a high temperature, more molecules have enough energy to get over the activation energy. And if you have a low temperature, you have fewer molecules making it over the activation energy. Of course, the number of molecules colliding, that has to do with probability. There's more probability for them to occur. It's just if concentration is high, you're going to have more collisions that give more opportunities for the reaction to occur. And then there's catalysts. How do they affect the reaction? The definition of a catalyst is something that participates in the reaction but is unchanged by it. The way that a catalyst works, we usually say that they speed up reactions. And the way that they speed up reactions is they lower the activation energy. When they participate, somehow they lower that activation energy. And as a result, we see a faster reaction. The energy change, energy before and energy afterwards, is exactly the same as without the catalyst. It's just the activation energy is lowered. So now, with what you know, which reaction will be faster? One at 25 degrees Celsius or one at 37 degrees Celsius? Well, this is the higher temperature, so that's faster. Which one's faster? Higher concentration, right here, or lower concentration? Of course, it's a higher. And then last of all, look at these two reaction profiles. Which one is the faster reaction? Well, if I look at this, you can see this one is exothermic and this one is endothermic. Well, that has nothing to do with whether the reaction is fast or not. What controls the speed of the reaction is the activation energy from here to here and from here to here. The exothermic reaction has a larger activation energy. This endothermic reaction has a shorter one. Now, it varies for every reaction. It's not always going to look like this. What you do is you look and you say that has higher, that has lower activation energy, so this one will be faster. As important as energy is, the randomness of the conditions of a reaction is just as important. We call this randomness entropy, and there's actually a thermodynamic law stating that the energy of the universe, the entropy or randomness of the universe is increasing. So we don't ever become naturally more ordered. That doesn't happen. If you look at taking randomness into account in a reaction, we've got to consider both heat and randomness or entropy. And the way that we do that is in a sum called the free energy. So in this free energy, we have both the randomness and the heat changes. So this free energy is expressed as a delta G. That's a change in free energy. And that's really what we need to look at in reactions to determine whether or not they're going to go or not spontaneously. When you have a loss in free energy, so a reaction gives off free energy, you have a negative change in free energy, and the reaction goes spontaneously. So the change of randomness and heat together causes spontaneous reaction. There is something called endergonic, and what happens in those reactions is the free energy change is positive, and it's not spontaneous, meaning that you can't go without forcing some energy into the reaction to make it go. When you have a spontaneous process, it just continues on going once it started. Now, there's an activation energy. So like with burning alcohol, if I have just plain alcohol on the counter with oxygen around, it doesn't spontaneously start burning. I have to add a little heat to it, and then it'll start to burn, and it burns all on its own until it's gone, unless you exert an effort to put it out. And so once you start a spontaneous reaction, it just continues. So the free energy predicts the spontaneity, but it does not predict how fast it's going to go. Some spontaneous reactions, for instance, carbon-14 decomposes, and for half of it to be gone, it takes more than 5,000 years. That's a very long time, but it's spontaneous. But then there's some non-spontaneous reactions that occur readily just because you're putting energy in. For instance, a plant will absorb light energy and form glucose. The formation of glucose from carbon dioxide and water is not spontaneous, but the plant will take the energy and use it to do a non-spontaneous reaction.